Hello, today we're going to do an introduction to logic gates. This is going to be a very simple introduction, and once again please ignore all the pencil lines that you can see, which simply will be a guide for me when I actually deliver the video. To understand logic gates, we really need to understand how transistors work, and that was covered in my video Atomic Physics 3 Semiconductors, Diodes and Transistors, and there is a link to that video on the screen. But you may recall that I showed that there is a device called an NPN device, which is made up of semiconductor material. This is N, this is P, this is N. And the point about this type of device is that if you put a voltage across that device, plus, minus, then you might expect that electrons will flow towards the positive charge. But in fact, they don't, because there's what's called a depletion layer, which builds up at this junction, and which I describe in the earlier video, that essentially stops the electrons from flowing. But if you put a positive charge at that point, then the electrons will indeed flow across. And so this is essentially a switch. If there is no positive charge at that point, no electrons flow. In other words, no current flows. But if you put a positive voltage at this point, then the electrons will flow and a current will flow. So it's a very simple transistor switch. We call this part of the transistor the emitter, because that's where essentially the electrons are emitted from. We call this part the collector, because it collects the electrons, if you like. And we call this part the base. Sometimes it's called the gate. Now, in electronic circuits, you will find that a transistor is usually represented by a symbol of this kind of form. And in this case, this is the emitter, this is the collector, and this is the base. So this is just a schematic representation of this semiconductor material here. And the same principle applies, that if there is a voltage, you might have, it varies for different transistors, but let's say you have 5 volts here and 0 volts here, then, and we better join up the wires so that there is a link, and the position is that no current will flow. The electrons are going in this direction from the emitter to the collector, so the conventional current is coming in this direction down the voltage. So no current will flow through that transistor if there is no voltage on the base. But if you put a voltage on the base, then a current will flow through the transistor. So what you can say is, if there is no voltage on the base, then the switch is off, because no current will flow through. So insofar as that transistor is acting as a switch, it's off, nothing will flow. And that is often given the symbol 0, or sometimes called false. On the other hand, if there is a positive voltage on the base, then the switch is on, and that is given the representation 1, or true. All these schematic transistor diagrams that I draw in this video will be in this form, with the emitter here, the collector here, and the base here. Now, since we are looking at logic gates, which are based on transistors, we must just temporarily abandon transistors to understand a little bit about what logic we're talking about. And this is known as Boolean logic, or Boolean algebra. And I can try to describe it by imagining that there is a playground, and that there are children playing in the playground, and some of those children are wearing red jackets, and some of the children are wearing black shoes. This group of children are wearing red jackets. This group of children are wearing black shoes. And this group in the middle are wearing red jackets and black shoes. So if I shade the area, then what you've got is that this shaded area is children wearing red jackets and black shoes. This group are children wearing red jackets but not black shoes. This group are children wearing black shoes but not red jackets. And all round the outside are children who are neither wearing red jackets or black shoes. Here's the self-same playground again. And here are the same groupings. But this time I want to know who are the children who are either wearing black shoes or red jackets or both. Then the answer will be everyone inside the two circles, because they're either wearing red jackets or they're wearing black shoes or they're wearing both. And the final question, just for these illustrative purposes that I might come up with, is how many children are not wearing red jackets or black shoes? And the answer to that is everybody outside the circle. And in terms of logic, this is known as an AND, because what we're saying is red jackets and black shoes. This is known as OR. In other words, either you're wearing red jackets or you're wearing black shoes, or maybe you're wearing both. And this is known as NOT. That is to say, you're not wearing a red jacket or black shoes or both. Now what logic gates do is they translate that Boolean logic into an electronic form. I'll explain later in the video exactly how you construct these gates using transistors, but let's just think about the different types of logic gates you can have. And there are 7 basic logic gates. The first gives effect to this logic, the AND logic. It's actually called the AND gate. Its diagrammatic form is something like this. It has 2 inputs and 1 output. And that's called the AND gate. And what it means is that you've got 2 wires coming into a device. We'll actually design the device in a little while, and 1 output from the device. In here there's some electronics, which I haven't told you about. But the idea is that if both inputs have got positive voltages, then there will be a positive voltage out. But if either one or both have no voltage, then there will be no voltage out. So in other words, you only get a positive voltage out if both the inputs have got positive voltages. If one or both do not, you won't get a voltage out. So that's a piece of logic. It tells you that if you get a positive voltage out, it must be because both of these have got positive voltages. The next electronic device gives effect to the OR option, and that is called the OR logic gate. And the diagram for an OR gate looks something like this. Again, it has 2 inputs and 1 output. And now the idea is that you'll get a positive voltage output if one or both of these inputs has a positive voltage. So if neither has a positive voltage, you get no output. But if just one of these has a positive voltage, or both, then you will get a positive voltage out. The next device gives effect to the NOT arrangement here. And again, this is an electronic device. It's called the NOT gate, and its symbol looks something like this. It only has 1 input and 1 output. And the idea is that whatever the input is, the output is the opposite. So if the input has a positive voltage, the output would have no voltage. If the input has no voltage, the output will have a positive voltage. Whatever this is, it's the opposite of this. And it's often called an inverter for that reason. Now there are 4 more fairly common gates. The next one is called the NOR gate. and that is drawn rather like an OR gate. Here's the OR gate, so far it looks the same, but what you do is you put a little circle there, and that tells you that it's a no, it's a not. So it's a NOR version of the OR gate. And what this means is that you only get a positive output if both of these have no voltage in the input. So if there's no voltage here and no voltage here, you get a positive voltage out. But if either or both of these have a positive voltage, you get nothing out here. The next logic gate is called the XOR gate, and that has a symbol that looks like this, rather similar to the OR gate, except it's got this extra line here. It also has two inputs, one output. And what an XOR does is it gives you a positive output if one of these inputs is positive, but not both. So if both are 0, you get no output. And if both are positive, you get no output. But if one of them is positive and one of them is 0, so that could be positive, that could be 0, or that could be positive and that could be 0, then you get an output. And then there's the kind of opposite of that, the XNOR, which looks exactly the same as the XOR, except that it has the little circle on it. So it has two inputs, one output, and this is the reverse of this. This reverses this. So in other words, this will only give you a positive output if both the inputs are positive voltages or both the inputs are 0 voltages. You will get a positive voltage out. But if one of them's positive and one of them's 0, you won't get anything out. And that's precisely the opposite of this one. And then the final one in the basic series of 7 is called the NAND Gate, which kind of says not and. And its symbol is very similar to the AND symbol. It has two inputs, but because this is the AND symbol, because it's a NAND symbol, of course it will have the little circle to indicate. And what that will do is it will give you a positive output if either or neither has a 0 voltage. It will give you 0 output if both of these are positive voltages. But if one is a positive voltage and the other is 0, or they're both 0, then you'll get a voltage out. And in that respect, of course, it's just precisely the opposite of the AND gate. The AND gate, you only get a positive voltage out if you have two positive voltages coming in. In this case, you get no voltage out if you have two positive voltages coming in, but if you have either one or both as 0 voltages, you'll get a positive voltage out. Now I'll just give you an illustration of how you can use these devices to build a very, very, very simple computer. Suppose we wanted a computer that would enable us to solve the equation A plus B equals C. And we're going to be very simple here because the only values that you can have for A and B will be 0 or 1. So A and B can be 0 or 1, which means that the value of C can either be 0, that's if A and B are both 0, or the value of C can be 1, if A is 1 and B is 0, or vice versa, or the value of C could be 2 if both A and B are 1. And so if we put that in a simple table where we put the values of A, B and C, then we say that if A and B are both 0, then C will be 0. If A is 1 and B is 0, then C will be 1. If A is 0 and B is 1, C will be 1. And if A and B are both 1, C will be 2. And we're going to build a computer that will do that calculation for us. And we're going to use logic gates to do it. So here is the device that we're going to build. We're going to have an XOR gate here. We're going to have a AND gate here. And we're going to have a NOR gate here. We're going to have, let's just move that up so you can see it. We're going to have two inputs, and they are going to represent our values of A and B. And if there's a positive voltage, then that represents the number 1. And if there's no voltage, then that represents the number 0. So in other words, we're going to either put a positive voltage on A or not, and a positive voltage on B or not. And the positive voltage represents our number 1, and if we don't put a positive voltage on, that represents the number 0. So we're now going to feed these cables through to all of our logic gates. We're also going to feed the B through to all of the logic gates. So now we've got A and B feeding through to each of our 3 logic gates. They are all going to have outputs, and what I'm going to do is to send those outputs to a light emitting diode. These are diodes which will glow red, or any colour actually, but red is a common one, if there is a voltage coming down the line, but they won't glow if there isn't. Now what does an XOR device do? Let me just remind you. That will send a positive voltage out if one of these is positive and the other isn't. If both of them are no voltage, or if both of them are positive voltages, you get no output. But if one of them has a positive voltage and the other one doesn't, then you will get a positive voltage out and the light emitting diode will light up. Well, if one of them is positive and the other one is not, you've essentially got 1 plus 0. So this is essentially the answer 1. What about the AND gate? Well, the AND will only put out a positive voltage if, I missed an input there, if both the inputs are positive. Alright, so that means that A and B both have to be positive voltages. So A has to be 1 and B has to be 1. So this is essentially the answer to 2. If this lights up, it must mean that there's a positive voltage on A and a positive voltage on B. And what about NOR? Well, NOR will only send out a positive voltage if both the inputs are 0 volts. If either or both have got positive voltages, you'll get no output. So the only way this light emitting diode is going to light up is if both inputs have no volts, and that means they represent 0. So 0 plus 0 is 0. So what you do is you take your inputs A and B and you put whatever you like. You can put, say, a positive charge on A and no charge at all on B. And what will happen is that you will get no output from AND because they both have to be positive, No output from the NOR because both would have to be 0. So these two transistor light emitting diodes do not light up. But the XOR will light up because the XOR says one but not both of them has to be positive. And when that lights up, you have added 1 and 0 to make 1. Now that is a very long-winded way of adding together two numbers which can either be 0 or 1. But that is what the heart of computers do, except they have millions of these logic devices that are handling information very fast. So now let's see how we might actually design these logic gates using the transistors. And we're going to start with the NOT gate. And what we mean when we talk about the NOT gate is that the output, which we usually refer to as Y, is equal to not the input. and if the input is labelled by A, then it's generally said A with a bar over means not. So the output is not the input. That's what we mean. And we're going to start off with a transistor with a base input, and we're going to go up via a resistance to a 5-volt battery, and this end we're going to come down to 0 volts, which means essentially it's grounded, so this is 0 volts, and we've got an output that we'll take here to, we could take it to say a light emitting diode, so that diode will only light up if there is a positive voltage coming out of the output. Now, what will happen? Let's suppose there is no voltage on the base. If there is no voltage on the base, this switch will be open. In other words, no current can flow through the transistor because there's no voltage on the base. And that means that there will be a positive voltage on this output because this is at 5 volts. Some of that will drop across the resistance, but there'll still be a positive voltage. We don't need to worry about what it is. There will still be a positive voltage here, and that means that the transistor will light up. So if there's no voltage coming in, there will be a voltage coming out. Now let's look at it the other way. Suppose there is a voltage coming in. Well, if there's a voltage coming in, then this switch closes and a current can now flow through the transistor. And if a current flows through the transistor, then since this point is 0 volts, this point also will be 0 volts. And so you've now got a positive voltage on the base, the input, but now no voltage on the output because a current is flowing through here, and so essentially this and this are at the same potential. And that potential is 0. And so this potential is 0, and the whole 5 volts is dropped across the resistance here. So this is simply an inverter. And what you can do is to draw what's sometimes called a truth table. If you look at the input, which we'll call A, and the output, which we'll call Y, if the input is 0 volts, then you will get a positive voltage out, which we denote by the number 1. On the other hand, if you have a voltage on the input, you'll get no voltage on the output. And so this is an inverter. Whatever you put in the input, you get the opposite in the output. And this is essentially known as a truth table. And we shall be drawing more of these for other devices. The actual symbol for the NOT gate is the triangle with the little circle on the end. And when you draw a triangle with the little circle on the end, this bit in the middle, the transistor and the resistance, is essentially the component that is creating the NOT gate. And here is the input here, and here is the output here. A single input, single output. You do, of course, have to power it, and that's what this 5 volt, probably a battery of some kind, is doing here. But that's just the power. This is the input, this is the output. Now let's move on and design an AND gate. So this is an AND gate, and that is usually written as Y is A dot B. That's the standard way of defining that the output is A and B together. And once again we have our transistors. This time we're going to have 2 transistors, and they are connected together. This one goes up to the 5 volt battery. This one comes down through a resistance to 0 volts, so that's essentially grounded. Better connect this up here. And our 2 inputs are essentially the 2 base inputs to the 2 transistors. And we're going to take the output at this point here. That's our output. And once again, you can send it through a light emitting diode if you like. I'm not going to draw that in here. What we're now going to look at is the logic. If you have no volts at all on these two inputs, then these two transistors, which are acting as switches, will be open. So no current will flow through the transistors. And consequently, since this point here is at 0 volts, then everything up to here will be 0 volts. This is essentially a switch that's open. No current can flow this way. And so all of this is going to be at 0 volts. So the output will be 0. So if the two inputs are 0, the output is 0. What happens if one of these is open? Sorry, one of these is a positive voltage and the other one has 0 volts. Well, if this has a positive voltage, a current can flow through that transistor. But if that is 0 volts, it doesn't do it any good because the current cannot flow through this transistor. And vice versa. If this has 1 volt, the current could flow through this transistor, but if this has 0 volts, it can't flow through this one. So even if you have one of them with a positive charge and the other with a a positive voltage and the other with a 0 voltage, still no current can flow, still therefore this will be at 0 volts. But what happens if both have positive voltages? Then the switches will close, a current can now flow, the potential difference will fall across the resistance, but this output will now have a positive voltage because it's connected to the 5 volts up here through the switches which are now closed. So if and only if both of these inputs are positive, you get a positive output, and that's the AND gate. And the symbol for the AND gate is something that looks a bit like this. So when we draw the AND gate in this form, what we're actually saying is that here are the two inputs, here is the output, and this two transistors and resistance are what's contained within. So once again we can draw our truth table for our inputs and our output. Our inputs are A and B and our output Y. If the inputs are both 0, the output 0. If one of them has a positive voltage and the other doesn't, the output is still 0. If it's the other way round, the output's still 0. It's only if both A and B have positive voltages that you will get a positive voltage out. Let's move on and design the OR gate. And this is often represented as Y, which is the output, equals A plus B. And of course that means that either or both are true. Either A or B inputs will be a positive voltage. And once again we need two transistors with the two inputs here, A and B. These are the two inputs. This time we're going to connect this to the 5 volt battery, and here we're going to connect this via a resistance to 0 volts. But what we do here is we send this up to the 5 volts that way, and here we bring this out down to an output which is coming here. Now let's draw our truth table as we go along. The inputs A and B, the output is Y. Let's now ask what happens if A and B are both 0. If A and B are both 0, then these two transistors acting as switches are both open. That means that no current can flow this way and no current can flow this way. So in other words, this output line here will be at exactly the same voltage as here, and that's 0 volts. So if A and B are both 0, no current can flow through that transistor, no current can flow through that transistor, therefore the output is also 0. Now what happens if A is 1, in other words, if A has a positive voltage but B doesn't? Well, let's do B first of all. B, no current flows, so consequently nothing happens as far as B is concerned. But if A has got a positive voltage here, a current flows through the transistor and right the way down to the 0 volts. I'll just show you the path again through that transistor, which is now closed. The switch is closed because there's a positive voltage here. So through the transistor, right the way down to the ground here. And that means that there will be a potential drop across the resistance, but there'll be a positive voltage on the output. So there's a positive voltage there. And I think you can see fairly easily that the same is true if it's the reverse. If A now has no voltage, there'll be no current going that way. But if B has a positive voltage, then the current can flow through the transistor and down here. The potential is dropped across this resistance, which means that the output here has a positive voltage. And obviously if A and B both have positive voltages, then the current can flow both this way, and that means there will be a positive voltage on the output. So we've now got a device which says if you've got no voltage on the inputs, you won't get a voltage on the output. But if you've got a voltage on one or both of the inputs, you will get a voltage on the output. And the symbol that we use for an OR gate is the one that I drew before, and that is this one. Now in fact we can use this description of the OR gate to create our NOR gate, because you don't do very much more with a NOR gate. With a NOR gate you simply add a further transistor, and you have the output from the OR gate going into this transistor. And then you go up through a resistance to the 5 volt level, and you come down here to the 0 volt level. And this, of course, is simply a NOT gate. That's exactly what we drew here. Transistor and a resistance is a NOT gate. So this is a NOT gate. So in other words, whatever the output is, we'll take the output there. Whatever the output from the OR gate is, the output from the NOT gate will be the opposite. So let's now look at our truth table, and we can see that this is the output from an OR gate. But now let's look at the output from a NOR gate. Well, it will always be the opposite of whatever the OR gate is throwing out, because we're putting it through an inverter. So if it was 0 here, it'll be 1 here. If it was 1 here, it'll be 0. If it's 1 here, it'll be 0. If it's 1 here, it'll be 0. It's precisely the opposite of the OR gate, because we're putting it through an inverter and taking the output out here. And that output will be the opposite of the input. And the input is effectively the output of the OR gate. And so you've now got a NOR gate, and a NOR gate symbol, of course, is the same as an OR gate, but you put a circle on it like that. And the representation of a NOR gate is y equals a plus b, which is the same, of course, as the OR gate, but you put a line over the top. Remember that a line over the top, in the same way as we did it with the NOT gate, a line over the top, I said, meant that there's a NOT element to it. So here we've got a NOT OR. This is the OR gate. This is not an OR gate. It's the opposite of an OR gate, giving us the exact opposite output to what you would get from an OR gate. And now we're going to look at a NAND gate. Remember, that's the NOT AND. So Y, the output, is equal to A dot B, which is the same as for the AND gate, but because it's a NOT, you put a line over the top. And the way we design that, we again need 2 transistors. and each of those will have an input, and those are going to be our inputs A and B. We're going to go up through a resistance here to the 5-volt level, and we're going to connect these two, come down here to a 0-volt level. So essentially, once again, we've put a battery between the two devices. And this time we're going to take our output along this line here. And now we'll draw our truth table as we go along. A and B are our two inputs, and Y is our output. So let's suppose that both the inputs are 0 volts. If that is the case, that switch is off, no current can flow through here, and consequently the current will flow this way. Some of the voltage will be dropped across this resistance, but there'll still be a positive voltage here because no current can fall down here, so there's a positive voltage. So if there's no voltage on the inputs, there will be a voltage on the output. What happens if A is 0 but B is a positive voltage? Well, the current still can't get down because it can go past it can't even get past the A transistor, let alone go through the B one. And so consequently, there's no current flowing right the way down. The current will flow this way. There will be a voltage drop across the resistance, but there'll still be a voltage here. And similarly, the other way around, if A and B, A has the positive voltage, B does not, then the current will flow through the A transistor, but it can't get through the B transistor because that transistor as a switch is open. Consequently, the current can go this way, some voltage drop across the resistance, but there's still a positive voltage here. But if both A and B have got positive voltages, both those switches will close. The current will now flow straight down here. The entire voltage will be dropped across that resistance, which means that this point here will be the same potential as this point here, because this is just the equivalent of a straight wire. The current is flowing straight through. So this potential, which is 0 volts, is the same as this potential, and therefore the output will be 0 volts. It's a NAND. What it means is that you get an output for everything except where both the inputs have got positive voltages. And remember that the symbol for a NAND gate is the same as the symbol for the AND gate, except it's a not, so it gets a little circle and then the output. We've done 5 of the gates, we've just got 2 more to do. The next one we're going to do is the XOR gate, and let's move that over so you can see it, and that has representation of Y equals, Y is the output, don't forget, A plus in a little circle B. And that means that either one of the inputs is positive but the other isn't. So one can be positive but not both. And here we actually have to use other gates. They will contain transistors, but we need to use actually 4 NAND gates to create an XOR gate. And that's how you start to see how these gates build up in logic terms. So let me draw my 4 NAND gates. 1, 2, 3, 4. And we're going to connect them this way. Here is the input. Well, actually the input is going to come here. And we're going to split the input like this. The output that comes from this NAND gate becomes the input for this NAND, or these NAND gates, and then the output from those NAND gates become the input for this NAND gate. So here's the input, this is A and this is B. We split it so that we send the input through this NAND gate. We also take A and B into these NAND gates, and we take the output from the NAND gate into these NAND gates, and then we take the output from both of those NAND gates to become the input to this NAND gate, and finally we get an output from there. So let's try to create the truth table. We've got A and B, and we've got Y, which is the output. And let's start off with A and B both being 0. And remember that the point about a NAND gate is that you get an output in all circumstances unless both the inputs are positive. So we've got 0 coming in here, 2 zeros, that will give us a positive output. So we'll now have a positive output going in here with a 0 coming in here. A 1 and a 0 still gives you a positive output. Similarly here, you've got, remember we had a positive output going in with a negative, that still gives a positive output. We've now got positive coming in here, positive coming in here, and 2 positives going through a NAND gate will give you a 0 output. Hope you followed that. Now let's do the situation where A is 0 but B has a positive input. So A is 0 but B is positive. So in this one we've got a 0 and a positive. Well, that means you'll get a positive out. A positive out coming in here together with a 0A will give you a positive out. So that's a positive coming in here. What about at this end? Well, B, we said, remember, is positive. So B is positive. The output from here is positive. So we've now got 2 positives going in. That means you're going to get a negative, you're going to get a 0 coming out. You had a positive coming in here, a 0 going in here, a positive and a 0 will give you a positive output. If you do it the other way round, I think I don't need to talk you through it. It's obviously symmetrical. It's going to be exactly the same. So there is going to be a positive output coming out here. And the final set of situations is if both A and B have got positive inputs. Well, what's going to happen? 2 positive inputs coming in here will give you a 0 output because that's the consequence of a NAND gate. A positive input and a 0 input will give you a positive output. Same applies here. 0 out, positive, 0 out becomes 0 in plus the positive in gives you a positive out. Positive and positive going in gives you 0 coming out. So you get 0 coming out. And that is your XOR gate. You get a positive out if one or the other is positive, but not both and not neither. And the diagram which reflects the XOR gate is this one. And that just leaves us with one more to do, which is the XNOR gate, which is Y equals A plus B with plus in a little circle, but we put a line over it to show that it's a not. And how do we create that? Well, I don't actually have to draw another diagram, you'll be pleased to know. All that you do is you take the output here and you put it through a NOT gate. And if you put it through a NOT gate, all that will happen is that the output from the XOR gate will be, as it were, inverted. So whatever you get out of an XOR gate will be the opposite of what you get out of an XNOR gate. So down here, this is the XOR output, this is the XNOR output, Y, and that will always be the opposite to what you get out of here. So that will be 1, 0, 0, 1. And the symbol for an XNOR gate is the same as for an XOR gate, but of course it has the little circle at the end. So an XNOR gate will give you a positive output if either both the inputs are 0 or both the inputs are positive. But if one is positive and the other isn't, you will get no output from the XNOR gate. Now, just to say that, of course, some of those gates you didn't actually need to use transistors. You could have used diodes. This is a perfectly respectable OR gate. You put your inputs through two diodes and join them together. Here is the input A, here is the input B, and here is the output Y. If A is 0 and B is 0, the output Y will be 0. But if A is positive and B is 0, then a current will flow through here and you'll get an output. If A is 0 and B is positive, you will get a current flowing through here and Y will be positive. And if both of them are positive voltages, currents will flow and Y will be positive. And that is essentially an OR gate. But that works for OR okay, but you can't use diodes for some of the other gates that we've described. You have to use transistors. And finally, just to give you some flavour for how these logic gates are used in computers, they no longer use separate individual transistors. Instead, they use a process called photolithography, which is essentially a means of etching on semiconductor material, so that you create not just one transistor, but what's called an integrated circuit. And currently, you can get something of the order of the equivalent of 9 million transistors per square millimetre of an integrated circuit board. A scientist called Moore set up what became known as Moore's law back in 1965. He said that the number of transistors that you could get on a reasonable sized chip would double every 2 years. In 1971, they could get about 2,000 transistors on a chip by using this process of integrated circuit boards. Now, or in 2011, 2.8 billion transistors per chip are possible. And those chips go on to make microprocessors, and the microprocessors are what are at the heart of computers. And that all evolves from the essence of the logic gates that I've described today.